pi to the pi to the pi to the pi equals an integer? What kind of clickbait is this?
This video is sponsored by Jane Street. You might want a job, and they've definitely got some programs so you can find out more details at the end of the video.
Before we go anywhere with this, we have to deal with the estimate in the room. And that is everyone thinking, why don't we just calculate what it is and check if it's an integer or not? And if that was your first thought, you are in very good company. When I saw this on Twitter last month, one of the first responses was from Tim Gowers, a very serious mathematician. We're talking a Fields Medal winning mathematician. You don't get more mathy than Tim Gowers. And their first thought was, let's just calculate it, until they realized you can't. And this thing, it's an emotional roller coaster from beginning to end, from why it's surprising, to why it shouldn't be surprising, to why we can't calculate it, to why we probably can work it out. And you know what? We're going to deal with all of those in order. This whole situation is surprising because pi is a transcendental number. To recap, you've got the integers. These are whole numbers, things like 1, 12, 42, those sorts of numbers. You've then got the rationals. They're anything that's a fraction. So a third, 5/7, negative a 12th, anything like that. They're any numbers that can be written as a ratio. In fact, it's in the name. Rationals. It's got ratio in it. Oh. I know. Everyone remembers where they were the first time they noticed that. So the rationals actually include the integers, and these I consider the well-behaved numbers. You then have the irrationals, things like root 2. And root 2, it's pretty much root 2. And they're just things that aren't rational. So you can't write them as a ratio, but you can write them as the solution to a nice, neat equation. And then you have the transcendental numbers, things like pi, e, the natural log of 2. Numbers which aren't rational, and you can't write them as the answer to a neat, finite equation. You have to use something like an infinite series or something ridiculous to get these numbers. These numbers are very poorly behaved and they're very hard to get a grip on, which is why it's surprising that just by raising one of these to the powers of other transcendental numbers, you somehow get back to the most behaved. I mean, surely that's not going to happen. We're going to start one rung lower on the ridiculous number ladder and begin with irrationals. Can we raise an irrational to the power of another irrational and get a rational answer out the other side? Well, let's imagine root 2 to the power of root 2. Good rational number. Is that rational or irrational? Well, it turns out we don't actually have to know, because imagine we take that whole answer and we raise it to the power of root 2, another irrational number. And the way we're doing it here, that means it's now root 2 to the power of root 2 times root 2, which gives us 2, and root 2 squared is 2, an integer. So there you are. At some point, by starting with an irrational number and raising it to the powers of other irrational numbers, we get a whole number out the other side. So it does work for irrationals. Now we move on to our transcendental friends. This is even more straightforward. E, transcendental, to the power of the natural log of 2, transcendental, equals 2, an integer. I know. And before I put e and natural log of 2 up as transcendental numbers, no one bats an eye, but you raise one to the power of the other and you get an integer. Like, by definition, that's what the natural log is doing. Everyone suddenly startled. No, you can very easily raise a transcendental number to the power of another transcendental number and get an integer. So what on earth is going wrong with pi to the pi to the pi to the pi? Right, for simplicity's sake, how about we start by setting pi equal to 3? No, hey, I did not invite a stock audio studio audience in here to boo me. Now cheer it up. Better. Maybe a little too far. Okay, so we set pi equal to 3, and now we can work our way through calculating what this is, except when I was doing the root 2 thing before, I was kind of going from the bottom up. However, if there are no brackets or anything to indicate otherwise, if you've got a power tower, you actually work your way from the top down. At the very top, we have 3 to the power of 3, which is 27, 3 cubed. If we were using pi, pi to the pi is 36.432 and some stuff. So it's definitely bigger than 3 to the 3, but in the bigger scheme of things, not substantially so. We've now got 3 to the power of 27, which is a number just over 7.6 trillion. It's a 13-digit number. And we could have done this with pi. Pi to the pi to the pi is pi to the 36.43, etc., which is a number just over 1.2 billion, a number with 19 digits. The numbers are getting pretty big. Well, I say big numbers. We ain't seen nothing yet, because the next step is 3 to the power of that 7.6 trillion number. And if we were to work that through, the answer we get, well, this is not the answer we would get, that's how many digits would be in the answer. The answer would have over 3.6 trillion digits. And if we do the same thing with pi, we know the answer would have almost a billion digits. It's getting insanely big. Why can't we just calculate that? Well, to put it into context, I thought I would look at the current world records for calculating digits of just pi. Regular old pi. And in 2019, Emma set the world record at 31 trillion digits of pi. It was actually pi times 10 trillion digits. Amazing. And in 2020, Timothy pushed that out to 50 trillion digits. And it took Timothy 8 months of computing time to get 50 trillion digits. Emma was using Google computing resources, and that was only 121 days of calculation time. And we're talking tens of trillions here. The number of digits in pi to the pi to the pi to the pi, at least the whole number bit, that is in the billions of billions. That's about 1,000,000 times more digits. Not 1,000,000 times bigger, 1,000,000 times more digits. We simply cannot compute all of that. And the fact that it's pi makes it even worse than that. Allow me to explain.
Say what you want about 3, at least we know it exactly. It's equal to 3. And if we want to calculate 3 to the power of 27, that would start off easily enough, 9, 27, 81. However, the answers start to get very big very quickly. So to make our lives easy, we could decide to only care about the last 3 digits. Anything above that, we throw it away. So 3 to the 7, 2,187, that 2 is out of here. And importantly, we only have to multiply the bit that's left by 3 to get the next answer in the sequence. And we throw away any bit that's too big. And eventually we discover that 3 to the 27 ends in 987. We were able to throw away some details to simplify the calculation, but it means we don't get the whole answer at the other side, which is a problem here. We can only actually do that for the very last step. We need to know that entire 7 and a bit trillion number exactly, because we have to raise 3 to the power of that, but then we could do that simplification, and that's why we know that the answer of 3 to the 3 to the 3 to the 3 ends 6100739387, and that, for the record, is an integer. For pi, however, it's even worse. We could do that trick for the digits when the number gets bigger and bigger, going to the left. However, pi has infinitely many digits going the other way, and we don't know pi exactly. We only know a finite number of digits, so we have to use an approximation. And if we used only the first 7 decimal places of pi to calculate pi to the pi, the answer we get only matches the true answer for the first 5 decimal places. We now know fewer decimal places accurately. And that's going to be a problem. And by the way, I'm putting aside the whole world of number crunching hurt due to the fact that we're raising something to a fractional value, so we're technically taking a root, and there's a whole lot of computational effort there I'm not even going to touch. I'm going to focus on the very last step of this hypothetical calculation, where we've got pi to the power of over 1.3 billion billion. How accurate do we need to know pi to so we can do just enough of this calculation to check if the answer is an integer or not? Well, I tried a few much smaller values, and here's my results for the number of decimal places before you truncate pi compared to, if you raise it to different powers, how many decimal places in the answer match the true value. So for example, you take the first 5 decimal places of pi, raise it to the power of 6, only 2 of the places in the answer are correct. Now this is a bit off track, but I did this until I ran out of precision in Python. I then did some rough approximations using Wolfram Alpha until I hit the precision limits there. I did a plot of the number of digits in your approximation of pi compared to if you raise it to a certain power, there are no correct decimal places in the answer. And this is going to be one of the loosest pseudo conjectures ever. It seems from my very small, inaccurate results that it's about twice the number of digits. If you raise a truncation of pi to a power which is twice the number of digits in your approximation, you will get no correct decimal places in the answer. And I stopped there. I didn't compute any more with more precision. I didn't look at it theoretically. It was becoming a distraction. And for the record, people are going to try more values and they're going to send in critiques on my terrible, terrible conjecture. So, you know what? Send them to Math Plus Puzzles. I can't promise we'll get a chance to go through them, but if we do and there's something interesting in there, I'll do a follow-up video, but no promises. The point is, you need to know a lot of decimal places of pi if you want to get a sufficiently accurate result, particularly if the power you're looking at is 1.3 billion billion, and we currently only know pi into the tens of trillions. That is a big difference.
In short, there's no way we can calculate this in the conceivable future. However, there might be a workaround. Surely we could just prove mathematically that in theory, pi to the pi to the pi to the pi cannot equal an integer. Sadly, we can't do that. We don't have the mathematical tools. There's a lot we don't know about transcendental numbers. So while we know pi is transcendental and e is transcendental, we don't know if pi plus e is transcendental or not. We don't know if pi times e is transcendental or not. In fact, we don't even know if pi to the power of pi is transcendental. Even though we can calculate that one, so we know it's not a whole number, we don't know if it's transcendental. There's a lot we don't know, and there is one glimmer of hope. We have Chanuel's conjecture, which says things about when you combine numbers if you get a transcendental number or not. However, it is complex, I mean, literally, and it involves crazy things like field extensions, and I'll put a link to it in the description below if you want to have a closer look at it. The bad news is it came up in the 1960s, and now, over half a century later, the general consensus is we're still nowhere near being able to prove it. We're way off knowing if Chanuel's conjecture is true or not. So it turns out, humankind, we either have to get a lot better at mathematics and prove Chanuel's conjecture, or we need to get a lot better at computing. Until then, we have no idea if pi to the pi to the pi to the pi is an integer or not. The only thing we can say about it with absolute certainty is that the whole situation is just a bit irrational. Hey! Don't make me send you back for a refund.
This video was brought to you by Jane Street, the principal sponsor of the Stand Up Maths channel. I think they're great. They help make this whole channel possible. If you're considering a job or indeed career that involves solving complex mathematical problems in the financial world, Jane Street have an incredible range of programs so you can find out more. If you're a first or second year university undergraduate, you can go to the C program. Actually, if you're first year, you can also do the first year trading and technology program. They've got the Insight and In Focus programs because Jane Street are always striving to make their programs as accessible as possible. They've got internships, there's Focus, there's WISE, I've mentioned before, the Jane Street Symposium, so many options. These programs are hosted by the London and New York offices, and as you can see, a lot of them are currently accepting applications. If you're not looking for a job, then just, I don't know, appreciate the fact that they exist and they help make this channel possible. Maybe if you know someone else who wants a job or who's at university wondering what to do with their life, send them these programs. Just check them out. I'd appreciate it. I think Jane Street are great. They'll appreciate it. They make this channel possible. Check out the programs. That's what I'm trying to say. Jane Street, principal sponsors of the Stand Up Maths channel. Stand Up Maths was filmed in front of a canned studio audience sample pack. This has been a Stand Up Maths production for Stand Up Maths.